Today we're going to graph square root functions, and we're not going to use a calculator. That shouldn't come as a surprise to us since we did that with solving or graphing quadratics a couple of units ago. And the biggest part of square roots is knowing that square roots and squaring are inverse operations. So in a moment I'm going to be talking about where these points on our parent function came from. But in this lesson, we're going to explore all of the different transformations in a square root function. And the first one that we're looking at here is this f of x equals the square root of x. And it's actually the graph that's on your paper right there. And what I was just saying is that square rooting and squaring are inverse operations. Square root of 0 is 0. Square root of 1 is 1. Look at that point, 1, 1. Square root of 4 is 2. Look at that point, 4, 2. Square root of 9 is 3. That's where those points come from. 0, 0 on the parent function, 1, 1 on the parent function, 4, 2 on the parent function, 9, 3 on the parent function. When we look at the g function, g of x equals the square root of x plus 3 minus 2, that's when you might want to refer back to your transformations rules chart. The chart just reminds us of what the various things do to our function. So when we go back to graphing this one, we see that x plus 3 inside the function means that we're going to go left 3 units, and the minus 2 outside the function means that we're going to go down 2 units. We're going to take all of our points on this function and move them left 3 and down 2. So 0, 0 is going to move left 3 down 2. And it's going to become negative 3, negative 2. 1, 1 is going to move left 3 down 2. And it's going to become negative 2, negative 1. 4, 2 is going to move left 3 down 2. And it's going to become 1, 0. And 9, 3 is going to move left 3 down 2. It's going to become 6, 1. And here's our g of x function there. What we also want to do is we want to figure out, well, what's the domain of this function and what's the range of this function. And down here in part C it says, find the domain algebraically. Well, as we look at the domain, what we do is, to find the domain algebraically, we take the value underneath the radical, and we set it greater than or equal to 0. It's set greater than or equal to 0 because if the value were less than 0, we'd be taking the square root of a negative number, and the square root of a negative number gives us an imaginary value, and we want to deal with real numbers. But the range, what we have to ask ourselves with respect to the range is, do we have a high point or do we have a low point on the graph? We're going to look at that green point here on our picture. The range is a y value, and the y value of what I sometimes call the starting point of this function, the y value of that green point is 0. And as we look at that original graph that's already graphed on your paper for you, what we see is all of the values after that are above the green point. So this means that y is greater than or equal to 0. If we look at the graph that we just drew, what we're going to do algebraically is we're going to take x plus 3 and set it greater than or equal to 0. we're taking the value underneath the square root symbol to determine what our domain is. We're going to subtract 3 from both sides. We get x is greater than or equal to negative 3. We are looking at the black point in our blue graph here. And it makes sense because the x value of that black point is negative 3. And it's everything to the right. The domain goes left to right. Range is lowest to height. And again, do we have a high point or do we have a low point on the graph? Well, that black point is our lowest point on the graph. The y value of that point is negative 2. And all of those blue values are above that. So our range is going to be y is greater than or equal to negative 2. Number 2. Which of the following equations would represent the graph shown below? Use your knowledge of the transformation rules to help you. Well, in this particular one, once again, one of the things that I'd like to look at is where's the starting point of the graph? And I just put the starting point of the graph in a green point here. And if you look above in your first example, you got the parent function graphed. The parent function has the starting point at 0, 0. But now our starting point is over here 4 spaces to the left, which is one of our transformations. We actually have one more transformation on this graph. If you look again above at your example, your parent function, what you see is that this graph is flipped over, so it's kind of upside down. It's flipped over the x-axis. And when we take a look at our options over here, because this is a multiple choice question, left 4 means that we can eliminate option C and option D, because left 4 would be a plus 4. And then as we look at option B, the plus 4 is outside of the function, which means that this one would be up 4, so we can eliminate this function as well. And that must mean, and it does mean, that the negative outside the square root reflects over the x-axis, and plus 4 moves our graph to the left 4. Again, think about your transformation chart. We move left when we add something inside the function, and we move right when we subtract something in the function. Again, how do we calculate the domain of a function? Well, we take the value underneath the square root, and we set it greater than or equal to 0. This puts us in set notation. We subtract 2 from both sides, get x greater than or equal to negative 2. And it doesn't matter if we have something outside of the function. The domain is determined by the value underneath the square root. 3x minus 2 is greater than or equal to 0. We add 2 to both sides, and we get 3x is greater than or equal to 2. Divide both sides by 3, and its x is greater than or equal to 2/3. Once again, calculating the domain algebraically, we take the value underneath the radical, and only the value underneath the radical, and we solve it. Solve it the way your Algebra 1 teacher taught you to solve it. but I'm going to leave my letter on the left. I'm going to subtract 8 from both sides. We get negative 2x is greater than or equal to negative 8. To solve, we're going to divide both sides by negative 2. And the thing is, when we divide an inequality by a negative, the direction of the inequality changes. Then you do the math, as always. Negative 2 divided by negative 2 is positive 1x. Negative 8 divided by negative 2 is positive 4. So watch out for your signs. And in the inequalities especially. But the primary focus here is how do we graph? And again, we're going to graph without using a calculator. And I continue to refer you back to the transformation chart because this is going to look very similar to what we did in our graphing quadratics unit. So we need to be familiar with the various transformations when we graph. So our directions: graph the following square root functions, state the transformations that occurred compared to the parent function, which is drawn for us, and then state the domain and the range of the transformed function. So in our first graph here, we've got g of x equals 3 times the square root of x minus 4. And our first transformation is going to be determined by that 3. Please, please, please write the word vertical. We're not doing any horizontal stretches and compresses, but conceivably, if you continue to take math, you will. So you need to be able to distinguish between the two. But once again, our ordered pairs on our parent function are 0, 0, 1, 1, 4, 2, and 9, 3. The 0, 0 in this particular case isn't going to change. We're going to vertically stretch this graph by a factor of 3. That means that the y value of our points are going to change. And that one, our y value was 0, and 0 times 3 is still 0. But 1, 1. We're still going to go one space to the right, but instead of going up 1, because we're vertically changing this, it's going to be 1 times 3. For our second point. 1, 1 becomes 1, 3. 4, 2, we're still going to go right 4, but instead of going up 2, we're going to go up 2 times 3, and 2 times 3 is 6. And 9, 3, we're still going to go right 9, but instead of going up 3, we're going to go up 3 times 3. So this is going to be 9, 9. We vertically stretched that graph. We have one more transformation. In our transformation, it says x minus 4. Minus 4 inside the function means that we need to go right 4 units. And consequently, we're only going to be able to graph 3 points when we graph on this grid. But from the blue graph, 0, 0 is going to move right 4. So it's going to be graphed at 4, 0. 1, 3 is going to move 4 spaces to the right, and its order pair is 5, 3. 4, 6 is going to move right 4. So it's going to be at 8, 6. And then the 9, 9 would become 13, 9. $13, 9 won't fit on the graph. Now what we need to do, once we have the function graphed, is we need to go back and find the domain and the range. I'm gonna put that point there in black. That's our starting point now of the graph. The ordered pair of that point is 4, 0, and that's going to help us when we come over here and do our domain. Because domain is going to be an x value, and range is going to be a y value. So we're only going to deal with the x values on this first one. So the x value here is the 4, and then as we see, our graph is going to the right, so this is going to be x is greater than or equal to 4. Our y value is 0 from that starting point of our graph. And then all of the points are going to be above that. And above also means greater than or equal to 0. The key is identifying the starting point of the graph. H of x equals negative 1/2 times the square root of 6. The square root of x plus 6. First transformation is the negative. Negative is separate from 1/2. The negative is going to cause us to reflect over the x-axis. 0, 0 is going to stay the same. But our next point in our parent function, which is 1, 1, is going to flip over the x-axis, and it's going to become 1, negative 1. The point 4, 2 is going to flip over the x-axis and become 4, negative 2. The point 9, 3 is going to flip over the x-axis and become 9, negative 3. There's our first transformation. Again, let me try to emphasize that negative does something, and then the 1/2 does something else. So the 1/2 is going to determine our next transformation, which is a vertical compression. It's going to be very hard to see on the graph. The good news is that 0, 0 is going to stay the same. But what's going to change are going to be the y values. So we're still going one space to the right, but instead of going down 1, we're going to go down 1 times 1/2. So this next point is going to be 1, negative 1/2. The following point on our blue graph is 4, negative 2. We're still going to go 4 spaces to the right, but instead of going down 2 spaces, it's going to be 2 times 1/2. It's going to be down to negative 1. And then 9, negative 3. We're still going to go right 9 spaces, but instead of going down 3, we're going to go 1/2 times 3, which is 1.5 or 1.5. Again, very hard to see those points on my graph. They show up a little bit better on your paper. The negative does something, the 1/2 does something. And now we've got that last transformation, the plus 6, which is up 6. So we're going to move all of those points from our green graph up 6. 0, 0 becomes 0, 6. 1, negative 1/2 becomes 1, 5.5. 4, negative 1 becomes 4, 5. And 9, negative 1.5 becomes 9, 4.5. And there's our picture. Once we get it graphed to determine the domain and the range, Now look at this particular point that I just put in black. That ordered pair, once again, is 6. Nope, it's 0, 6. And that's going to help us determine the domain. Domain are the x values. Range are the y values. So the x value of that ordered pair is 0. The y value of that ordered pair is 6. So they coincide. When we look at the x values here, we're going to the right, which means that we're going to have x's greater than or equal to 0 for our domain. But for a range, all of those values, especially in red, are below the value of 6. So this is going to be y is less than or equal to 6. Flipping our paper over. One more here to practice. And hopefully some of the transformations from our quadratics, graphing quadratics unit, are coming back to you. But when I look at this one, the 2 out in front of the function is a vertical stretch. The parent function is there for us. 0, 0 is going to stay the same. We're going to go one space to the right, but instead of going 1 up, we're going to go 1 times 2. It's going to be 1 space to the right and 2 up. We're going to go 4 spaces to the right, but instead of going 2 up, we're going to go 2 times 2. So it's going to be, the point's going to be 4, 4. 9, 3. We're still going to go 9 spaces to the right, but instead of going 3 up, we're going to go 3 times 2, which is 6 up. And the vertical stretch shows up pretty well on our pictures, on the screen, on your paper. Second transformation. There's a negative inside of the function, which is going to reflect our graph over the y-axis. 0, 0 is going to remain the same. We're going to take our graph and we're going to flip everything over on the y-axis. So the point 1, 2 from our blue graph is going to become negative 1, 2. From our blue graph, the point 4, 4 is going to become negative 4, 4. From the blue graph, 9, 6 is going to become negative 9, 6. There's our graph reflected over the y-axis. We have one more transformation. Minus 2. It is outside the function, which means down 2. So we're going to take all our points from the green graph and we're going to move them down 2. 0, 0 is going to move down 2. Negative 1, 2 is going to move down 2 to negative 1, 0. Negative 4, 4 is going to move down 2 to negative 4, 2. And negative 9, 6 is going to move down to negative 9, 4. And that's our final transformation to draw our complete graph, so that we can now answer what's our domain and what's our range. And that point that I just put in black once again is important. Domain are the x values. Range are the y values. This ordered pair, if I can get it right this time, is 0, negative 2. So 0 is the x value. I'm putting that in for the domain. Negative 2 is the y value. I'm putting that in for the range. And then we just have to put in the appropriate inequality sign. Well, what we're doing here in the red graph is we're going towards the left. So for our domain, which is left to right, we're going to have values that are less than or equal to 0. For our range, after that black point, all of those values are above it. So it's going to be y is greater than or equal to -2. So there's the graphing. Again, I hope that that is familiar to you. As we finish here, should look remarkably familiar from the graphing quadratics unit again. Can we use our transformations to write down what's happening here? Our parent function is y equals the square root of x instead of y equals x squared. If we take a look at this one, y equals the square root of x, and the things that are going to change when we have a reflection over the x-axis, we're going to have a negative out in front of it. That's a reflection over the x-axis. Down 7 is also an outside feature. It means -7. Letter B, still once again starting with y equals the square root of x. But in this particular case, the vertical stretch by 3, well, that's going to be an outside feature. There's a vertical stretch by 3. The 5 is inside the function. This is going to be plus 5, all underneath the square root. And then up 2 goes in the same position that the down 7 went. It's going to be plus 2, outside of the function. Lastly, y equals the square root of x for our vertical compression. And then we put the vertical compression in. The vertical compression goes in the same place where the vertical stretch goes. 3/4, it's outside of the function. And a reflection over the y-axis happens inside the function.